This is a picture I took a few days ago, and within your life you've probably seen millions of pictures. But it seems like our brain has a nearly infinite capacity. We can keep seeing more images and it would never just take out space. And that's because of two reasons. Both our brain has really high capacity for storage, but it also uses some really clever, intelligence-based compression algorithm that operates completely differently to how algorithms like JPEG operates. Now the question becomes, can we use similar algorithms with artificial neural networks to compress images so we can store a nearly infinite amount of images on a single computer? This video is about AI compression algorithms. It's about the link between compression and intelligence, and how AI compression algorithms are insanely better than any traditional compression algorithm that we used so far, and why we don't use AI compression pretty much at all. Pretty much any image we see on the internet is an image that is compressed by JPEG. JPEG uses stuff like the resolution of the color and different frequencies of details in the image to be able to represent the same image with less data in a way that the difference would be indistinguishable to the human eye. But an important thing about JPEG is that it compresses the image without understanding what's in it. When you look at this image, you can see there is a tree and a sky in the image. And if now I will hide this image from you and I would ask you to imagine it from your memory, you would probably do a pretty good job at imagining this scene. But you would imagine the concept of those scenes, how they relate to each other, and in general how do they look. But you wouldn't remember pixel-wise values, you wouldn't remember the leaves and the exact position of each detail in a texture. And maybe you didn't even notice that I changed the image after I told you to remember it. And almost none of the pixels remained the same. So an ultimate compression algorithm would be able to understand what is perceivable to humans and be able to discard everything else. Let's talk for a second about the concept of entropy in data. You've probably heard about entropy in physics as a measure of disorder or how spread out energy is. And the entropy we will talk in this video is about entropy of information, of data. And you'll be surprised that it's actually the same entropy as in physics. But let's give a few examples of how we're gonna treat entropy. So let's define entropy as the minimum amount of information you need to describe a piece of data. And by that definition, this image, for example, has very low entropy, as all you need to describe the full image is not the pixel values, but just the interval of how often do you need to change from white to black. And this image has more entropy than the last one, because now we need to remember the position of each stripe to describe this image. And this one has even more entropy, as now we need to remember both the position, the height, and the size of each stripe. Now you can see that entropy is associated with disorder, as disorder has more information in it. It takes more information to describe. And we can define the task of data compression as trying to take a piece of data and represent it in a size that is close to the entropy of that data. Now let's take this image for example. It looks exactly like the first image, but it actually has more entropy. Each line is just moved a few pixels to the right or to the left, but it's imperceivable to humans. But even though it looks exactly like an image with extremely low entropy, it actually has a lot more entropy than the original one. But if we can algorithmically understand that this image looks extremely similar or imperceivably similar to another image that has a lot lower entropy, we can compress it as the other image and lose the offset of a few pixels to the right or to the left. but at the end compress it to a much smaller file size. So I would say this image has more entropy than the original one, but it has the same perceptual entropy. So our ideal compression algorithm would be able to understand what is the perceptual entropy of the data and represent it with that much information. And the more our compression algorithm is able to understand how our brain encodes information, the more we can represent this data as the limit of the perceptual entropy of that data. Or in other words, the limit of the minimum information that we can represent this image with without our brain understanding that it's a different image. And that's why AI compression is so powerful, because optimal compression algorithms ultimately require us to understand how our brain compresses information and emulate it. Let's approach the concept of AI compression by starting with autoencoders. While in some of my other videos I go into a lot more detail about what autoencoders are, for this video all we need to understand is that an autoencoder is a neural network that is trained to recreate the same data as its input. But the catch is that somewhere in the middle of the network there is a layer that is much smaller than the data itself. And usually just by training this network on a lot of images, the network is capable to reconstruct images almost perfectly while compressing them to a much lower dimensionality space in the middle. So you might think an autoencoder alone would be a great compression algorithm. But let me show you why you basically can't even compress anything with it. If we take a look at the middle layer, we will see that it's just a list of a lot of numbers, 6,144 in this case. And if we take a look at those numbers, we will see that they are just decimal numbers. So while it is less numbers, usually storing an image allows each pixel to be just from 0 to 255. But those high precision numbers require a lot more data to be stored. Because the limitation of any data we want to store in a digital computer is digital, means it's binary. We will need to convert it into just zeros and ones at a certain point. So when we train a neural network, we typically use very high precision numbers that takes a lot of data to be represented as binary. An important concept to understand when we want to store a number and not take as much data is quantization. One of the simplest examples of quantization is just taking a number and then cutting all the digits from a certain point. And we definitely can do that, and we will get a smaller file size, but we will get a significant reduction in quality. Because the training process of our autoencoder never included quantization. And the quantization method of just cutting the digits is very naive, as it relates to the number itself and not what it represents. So the question becomes, can we train the model to do quantization itself in a way that after the quantization, it keeps only the data perceivable to humans? Well, the answer is no, we can't do that, but we can get very close. And I want to show you one of the coolest algorithms we can put inside of an autoencoder to get very close to what we want. Now, let's look closer at the middle layer. Because it's 32 by 32 by 6, we can think of it as dividing the image into a 32 by 32 grid and assigning to each one of those boxes 6 numbers that describe this box. Now, with 6 dimensions for each one of those boxes, the model have a lot of flexibility to describe each square however it wants. Now, the human brain is not working like that. We can see concepts, we don't really see the image itself. So if we would try to describe how the brain works, we would choose a predetermined symbol to describe each one of those boxes. And that symbol corresponds to some concept that we learned from experience. Now, let's for 1 second assume we can create an algorithm that is doing the same thing, and try to understand how much data can we save in terms of compression. Now, if each of those squares correspond to a symbol, and all of those symbols are something that we learned in the past, this means instead of storing 6 high-precision decimal numbers for each square, we can store one small integer that we can use as an index to choose the right symbol. Now let's see how practically we can convert our regular autoencoder into what we call a vector quantized autoencoder that uses symbols instead of vectors in its latent space. Now, as we said, those symbols are something learned. We can't tell the model what is a sky and what is a tree. It needs to learn it by its own. Now, let's call all of the list of these symbols a magic color palette. Because you can imagine each one of those symbols as a magic color, like a color tree, where we can paint and then a tree will be where we painted. Now, to be able to store it efficiently, we want the size of the magic color palette to be a power of 2, so we can use a whole number of bits to store it on the computer. And because our autoencoder has a 6 dimensions per box in the latent space, each symbol of the magic color palette would be 6-dimensional. It would store inside of this symbol 6 numbers, which means there would be like 6 numbers associated with the symbol of tree, 6 numbers associated with the symbol of sky, and any of the other thousands of symbols that the model can learn would be represented by 6 numbers. This process of trying to make our autoencoder symbolic is called a vector quantized autoencoder. And this whole process is operated within the latent space. So you can see that our vector quantized latent space in the middle is in the tiny shape of 32 by 32 ints. And each one of those ints is associated with a specific symbol that is associated with a specific vector. So to start training our symbolic color palette, we'll start by initializing each one of the symbols randomly. Let's start by just focusing on the encoder part. The encoder part would output a 32 by 32 grid where each box in this grid contains a vector with 6 dimensions. To train the vector quantized layer, we will take each of these boxes and compare it with all of the symbols we have in our magic color palette. When we find the closest symbol in our magic color palette to this vector, we will replace the vector in our grid with the index of that symbol. And we will update that symbol to be a little bit closer to the vector that was stored in that specific box. Then we continue to collapse each vector into its corresponding symbol. And we repeat the process for millions of images, collapsing each box into its symbol and updating the symbols to represent patterns that are more common in those images. This grid of symbols is our latent quantized layer. And to decode it, we'll just replace each one of the symbol indices back with the vector that is stored within that symbol. And if we visualize our quantized latent space after training this model on a lot of images, we will see that the model learned to correspond each type of object in the picture with a different symbol, and that it learned to decode this symbolic latent space back into almost the same image. And the more colors in our magic color palette, or the more symbols we have, the more the model can represent different kinds of objects and recreate the image in a more accurate way. Like here, we can see that if we allow the model to use 1024 different symbols, the reconstruction is almost flawless. It looks almost identical, but it uses significantly less data to store this image. Let's again have a look at our visualization for the latent space. While it is insanely smaller than the original image, it can actually be even smaller. Because we can see that there is a lot of pattern here, like the fact that if one spot is a sky, most likely the spot to the right of it or to the left of it would also be sky. And that objects have certain shapes like the trees and the mountains. And when we see patterns, we know that the entropy of that data is much smaller than the actual size of the data. Or in other words, that we can actually compress it much farther. What our model did so far is it essentially erased most of the information that is unrelated to how the image looks to a human. But it didn't do anything about representing the information that is left in the most compressed way. But actually, now we can just use traditional compression algorithms on the quantized latent space that we have. And even just naively using something like PNG, a modern lossless image compression algorithm, would yield a really good compression to our latent space. But typically the latent space is compressed with much more statistically pure algorithms like Huffman coding or arithmetic coding, which I'm not going to get into in this video, but I left some links for other videos that explain it really good. Now, to make everything feel a little bit less arbitrary, I want to generalize what we did here and show you how almost every AI compression algorithm is following the same process, using different techniques and different models, but it's essentially the same process. So regardless of the data type, even if you want to compress, let's say, audio or a different kind of data, those are the steps to compress it with AI. Step 1 is dimensionality reduction. Both in this video and in general in almost any model that is doing data compression with AI, we use an autoencoder for this step. But essentially, the first task is to represent the piece of data with less dimensions. The second part is some kind of learned quantization. There is about 1 million different ways to do this part, and in this video I showed you the vector quantized autoencoder method to convert our latent space into symbols. And the last part is entropy coding, or in other words, just classic compression algorithms, where we try to represent this data with a size as close to the entropy of that data as possible. There is also a ton of different ways to do that, but I've seen arithmetic coding mentioned in a lot of different papers. Now let's look at an existing model that was trained in a similar way to our process and see how good it can be. Let's start with the model Hi-Fi-C by Google. Let's look at this image, for example, that was heavily compressed with JPEG to the point where the file size is really small, but there is a significant loss in quality. Let's see how the AI model would compare for the same amount of compression. We can see that the image looks absolutely perfect. And you might even think it looks too perfect, to the point that you think the AI probably hallucinated the image and the reconstructed version looks good, but nothing like the original. It is so indistinguishable, it's almost like magic for the amount of compression we've done. If you ever try and make a model, like the ones we discussed in this video, you would see that it's an immense challenge that requires a lot of both knowledge and problem-solving skills. And this is why I'm so proud to announce that this video is sponsored by Brilliant. Brilliant makes you better at thinking and problem-solving, with thousands of visual interactive lessons in math, science, programming, data analysis, and AI. Brilliant doesn't just let you watch video lectures. It lets you play with concepts and build your understanding from the ground up. It would help you build critical thinking skills, not by memorizing concepts, but by letting you solve problems. Learning just a little bit more every day is extremely important, both to your personal and professional life, and Brilliant helps you make a habit out of it. With Brilliant, you start with the fundamentals, but you can reach really serious learning goals. Wherever you are, you can learn on the go with Brilliant. So go to brilliant.org/Lahat and start learning for free today. And if you use my link, you even get 20% off on the annual subscription. Let's get back to AI compression. Now the question is, if it's so great, why don't we use it everywhere? Well, while making this video, this is the question I ask myself every 5 minutes. And I found 2 main reasons. The first one is that it's much more computationally expensive and slow And the second one is a lack of an ecosystem and standardization that allows different computers to agree on the same algorithm. But if you ask me, it's only a matter of time until it will become the standard. As computers are getting more and more powerful and those algorithms are getting more and more mature, standards will appear, and I would estimate everybody would use AI compression algorithms in the future. Working on those videos is one of the most joyful pieces of work I've ever done. And if this channel ever becomes successful, it would be a dream come true. And if you want to help the channel become successful, I think you already know what to do. Remember that life should be enjoyed, and I'll see you in the next one. Bye bye.